Hello everyone, welcome to our second to last chapter of this course. So in this chapter we are going to focus on sensation and perception. So sensation and perception basically refers to the fields that not only talk about how we take in sensory information, which is that sensation aspect, but also how we kind of convert that energy into neural impulses and interpret it in our brain. So that will be kind of more the perception aspect. So this is just an example of a very common visual illusion. So if you stare at this object for several seconds, it can actually change perspective after you stare at it for a few seconds. So you'll see that sometimes kind of the bottom box seems like it's the one that's closest to you, the bottom square, whereas if you stare at it long enough, sometimes the square that's kind of up to the top kind of pops out at you a bit more. It would be a lot easier if I could kind of show you what I'm talking about here. But this is just one example of how the same sensory information, so obviously we're taking in the same visual information from this picture, can be interpreted in different ways. So we can actually have different perceptions for the same sensory information. And there's a link here. Unfortunately, I can't really show you a YouTube video within a YouTube video, but what I want you to do right now is pause this video, and I want you to go to the news forum post where I posted about this video being uploaded, which I'll do directly after I finish uploading the video. And within that post, this link will be there. So I'd like you to take a few seconds right now, if you could pause this video and go and watch that video, because it'll illustrate something that's really kind of an interesting illustration of our attention and how it works and that type of thing. I don't want to give too much away, but it's something that I like to show my students every year at the beginning of this chapter. So if you could take a look at that, just make sure that you're following all the instructions in the video, and then we'll move on to the next slide here. So module 4.1 is on sensation and perception at a glance. So we're basically going to define some key terms related to sensation and perception and talk about some guiding principles that we use in talking about how we interpret the sensory data that we take in. So as I mentioned, sensation as a term deals more with the process of detecting external events with sense organs and turning those stimuli into neural signals. Perception, on the other hand, is attending to organizing and interpreting the stimuli that we sense. And then in between the two, we have a process called transduction, which is when specialized receptors transform the physical energy of the outside world into the neural impulses. So basically what happens is we take in that sensory information using our sense receptors, so that would be the process of sensation. Then that sensory information is converted to a neural signal so that it can be interpreted in the brain, and that's the process of transduction. And then when that information is sent to the relevant area of the brain for processing, and we decide what it is we're seeing or hearing or smelling or tasting, then that would be the perception part of the process. So you can see right here in table 4.1, there are a bunch of different stimuli that might affect our major senses, and then we have corresponding receptors for each. So obviously we know, for example, vision is light waves, and the receptor is a light-sensitive structure at the back of the eye, which we'll talk about later in this chapter. In hearing, we're going to use sound waves as our stimulus, and the receptors are actually small hair cells within our inner ear that respond to pressure changes in the ear, and so on. So we'll talk a little bit more about each of these different types of stimuli and receptors for our different senses. So this is just kind of a nice diagram that summarizes a bit about what I just talked about. So you can see the stimulus enters our system through our sensory receptors. Transduction takes that, light wave, sound wave, whatever, and converts it into a neural impulse so that can be translated in the brain. And then it is basically sent on to whatever area of the brain for processing. So if it's visual information, the light waves are converted into neural impulses, and then those neural impulses would travel to the occipital lobe. To our visual cortex. If it was sound waves, then they would travel, they'd be converted to neural impulses, and then they would travel to the auditory cortex from the temporal lobe. So you can kind of see how these three processes fit together. So our sense receptors, as I've kind of mentioned, are specialized cells located within the sense organs that convert the physical energy from the environment or body to electrical energy. so which is then transported as nerve impulses to the brain for processing. So in that way, we can kind of think of our sense receptors like military scouts. They report their finding to the sensory neurons, which are kind of like the field officers, who report to generals at a command station, which would be your brain. So you can kind of think of it as that process. The military scouts, those receptors, are taking in the information. They're reporting it to those sensory neurons, who are kind of shooting that information up to the brain. And then the brain is what kind of interprets the information and decides what to do about it. So our sensory receptors are most responsive to the initial exposure to a stimulus. So for example, leaving a darkened theater, you probably all had the experience, not that we go to theaters much these days, but you've probably all had the experience where you come out of a darkened theater and your eyes are they take a minute to adjust. So you're kind of squinting for a second, because at first that stimulus of kind of the light that's hitting your eyes is quite intense. But over time, the sensation eventually becomes less intense through a process known as sensory adaptation, which is the reduction of activity in sensory receptors with repeated exposure to the stimulus. So thankfully, a lot of the time, if we're exposed to a stimulus over and over and over again, say it's a dripping faucet or the sound of, construction going on outside or something like that, hopefully after a while we'll kind of have sensory adaptation occur, and we no longer have to pay such strict attention to that stimulus. So it becomes kind of less meaningful or less potent to us. So if the sensory nerves all use exactly the same form of communication, which we know they do, so they're all using neural impulses within the brain, how do we differentiate between the different sensations? So that's a very good question, because obviously we take this information in through these various receptors, the receptors for light waves are in your eye, the receptors for sound waves are in your ear, and so on and so on. But once we convert all those to neural impulses through that process of transduction, you might wonder how the brain continues to tell those different types of energy apart. So basically we have what's called the doctrine of specific nerve energies. So the different senses are separated in the brain. There are different sensory modalities that exist because the signals received by sense organs stimulate different nerve pathways, each leading to different areas of the brain. So for example, if you have that visual information and it enters into your eye and is kind of processed by the sensory receptors in the retina, then that information, when it's then transformed into a neural impulse, is going to get sent through the optic nerve to the visual cortex for processing. So because that information, even though it's converted into neural signals, just like all the other sensory information is, because it travels that specific pathway of the optic nerve to that specific area in the brain, the visual cortex for processing, that's how we know that it's still visual information. So we don't kind of get all the different signals mixed up. In the same kind of way, signals from the ear would travel the auditory nerve to the auditory cortex. So each type of sense has its own pathways and its own areas of the brain for processing. And that's kind of how we keep everything apart. Interestingly enough, these pathways aren't fully distinct in the developing brain. And so it's shown that perception is actually a skill that our brains learn through experience. So those pathways are strengthened over time. And it's actually very interesting that sometimes if you see someone who is born blind or born deaf, those areas of the brain that are no longer being used, so for example, in a blind person, the visual cortex, or in a deaf person, the auditory cortex, sometimes those parts of the brain can actually be used to help out with other senses. So sometimes they actually kind of transform their purpose, which kind of goes along with this point that those pathways aren't fully developed at birth. So in terms of measuring the senses, the field of psychophysics is a field of study that explores how physical energies such as light and sound and their intensity relate to our psychological experience of them. So if you were standing atop a mountain on a dark, clear night, how far away do you think you could detect the flame from a single candle? I'll let you think about that for a second. I'm guessing that most of your answers are going to be not very far, which would seem to be kind of intuitive. Actually, if it was a completely clear and dark night with no other objects obstructing your vision, you could actually detect the flame from a single candle at about 50 kilometers away. So our sensory systems in the human body are actually extraordinary. Another question might be how much perfume would need to be spilled in a 3-bedroom apartment for you to detect the odor. Again, you might think quite a bit for you to actually be able to kind of pick up on that odor, But studies have shown that just one drop of perfume being spilled in a 3-bedroom apartment could lead you to detect the odor from across the apartment. So each of these values represents what we call an absolute threshold, which is the minimum amount of energy or quantity of a stimulus required for it to be reliably detected at least 50% of the time it is presented. So when we say reliable detection, that means you're able to pick up on it at least 50% of the time that it's present. And so absolute thresholds can differ by person, age, and even species. So we know that, for example, dogs probably have, a stronger sense of smell than us. There are other animals who have, much better vision than us. So obviously absolute thresholds would vary from person to person and species to species. But the absolute threshold says this is the minimum amount of sensory information that we need to be able to identify that there was a change or there was something that, we heard or we saw or we smelled. So here's a little diagram that kind of shows you the absolute threshold. So if you have the first part of the diagram here, the chance of detecting the stimulus is less than 50%, so we'd say it's too faint to detect. If it's the second part here, it goes above 50%, so it's so intense that it's always or almost always detected. So our absolute threshold is the level at which the stimulus can be detected 50% of the time. So another way of measuring sensory sensitivity involves having a participant compare two stimuli and judge whether there is a difference between them. So instead of just saying whether a light or a sound or a smell was there or it wasn't, we can say, did it change? Was there any noticeable change in the sensation? So the difference threshold, or the just noticeable difference, refers to the smallest detectable difference between stimuli that can, again, be reliably detected at least 50% of the time. So in order to say that our detection is reliable, we have to be able to pick up on it at least 50% of the time. The difference threshold depends on the overall intensity of both stimuli. So if you think of this logically, if I have, a 10-gram pebble in one hand and a 20-gram pebble in the other hand, I'm probably going to pretty easily tell a difference between the two, right? One is double the other. So that difference of 10 in that case, of just 10 grams, would be well above, hopefully, my just noticeable difference. However, if I had a rock in one hand that was a kilogram, and then in my other hand I had one that was a kilogram and 10 grams, so 1.001 kilograms, then I'm probably not going to be able to detect that difference. So even though it's the same amount of difference, in terms of being that 10 milligram difference, I would no longer be able to detect that there was a difference between the two stimuli. So the overall intensity or overall magnitude of the stimuli will affect how much of a difference you need to be able to notice it. So in general, the greater the magnitude or intensity of the original stimulus, the greater of a difference between the two you're going to need to be able to notice it. And so another example will be with saltiness. If you put salt on French fries, it's going to be a lot easier to distinguish whether there was no salt versus 1 shake of salt than it would to distinguish the difference between 4 shakes and 5 shakes of salt. Right? So again, the fact that there is more overall in the second scenario means that you would need a greater amount of difference to be able to detect it reliably. So now we're going to talk about signal detection theory, which is actually one of my favorite things in this chapter. I think it's really interesting. So it basically relates to the fact that even though we just talked about those absolute and those difference thresholds, they don't take into account the participant's general tendency when uncertain to respond with either yes, there was something present, or no, there was not something present. So in other words, we're not taking into account whether the person is a habitual yay-sayer or a habitual naysayer. So some people might be kind of more conservative and maybe, they thought there was something there, but they're hesitant to say that they saw it if they're not 100% sure. So they're going to be more likely to miss out sometimes on detecting whether a signal is present. Whereas if you have somebody who's super eager and trying to impress the researcher, they might think that they saw something even when they didn't, and they're more likely to say that they saw something in that case because they're trying to make sure they kind of capture every single instance. So in that case, they'd be more likely to have kind of false alarms, but they'd probably be less likely to miss signals when they did occur. So basically, signal detection theory states that whether a stimulus is perceived depends on both the sensory experience as well as a judgment made by the subject. So it's not just about the intensity of the stimulus or the intensity of the difference between the stimuli. It's also about the judgment made by the subject and whether or not they're saying there was a signal or whether they're kind of hesitant to say that there was one. So therefore, detection depends not only on the intensity of the stimulus itself, but may also be subject to observer bias. So within signal detection theory, there are 4 possible sensory judgment outcomes. There's a hit, there's a false alarm, there's a miss, and there's a correct rejection. And whether you're able to detect a weak stimulus depends on things like your expectations, your arousal level, and your motivation. So I didn't explain those 4 because I'm going to show you a diagram now that illustrates what I'm talking about there. So here's a diagram that kind of shows you those 4 different responses within the context of signal detection theory. So this is really important for you to understand. So signal detection theory recognizes that a stimulus is either present or absent by relying on the sensory process, and that the individual either reports detecting the stimulus or does not, which is the decision process. So we see here, if the question is there a bear in the woods? And the answer to the question is yes, and the individual's response is I hear something, well, that would be a hit. So they correctly said that the stimulus was there. He was right, he did hear the bear. If there is not a bear in the woods, but the individual says I hear something, well, that's a false alarm. So there wasn't a bear there, but he said there was one. So wrong, he must be imagining it. If the answer to is the bear in the woods is yes, but the individual says I don't hear anything, well, again, that's an incorrect answer, right? That would be a miss. So it was there, and he said it wasn't there. So therefore, he didn't hear the bear. And then the 4th option would be that there wasn't a bear in the woods, and the individual said, I didn't hear anything. And in that case, we would call it a correct rejection, because they said that there wasn't a bear, and there actually wasn't a bear. So therefore, they've correctly rejected the fact that there is a bear there. So you can see 2 of our 4 possible responses are correct, and 2 are incorrect. And so you should kind of understand this diagram and also kind of keep in mind those terms, the hit, the false alarm, the miss, and the correct rejection. So people who are habitual yaysayers will have more hits than naysayers, because if they're saying yes more likely, they're more likely to pick up on the ones that were there. But they should also have more false alarms as well, because they get too excited and say it's there even when it's not there. On the opposite side of that, naysayers will have more correct rejections than yaysayers, so they'll be more likely to say it isn't when it isn't there. But they should also have more misses. So if they're hesitant to report when they think they heard it, then they're more likely to miss it when it might have actually been there. So we can interpret the results of such a study by plugging the data into a mathematical equation that can separate out the estimates of a person's response bias from their actual sensory capacity. And obviously that is far outside of the scope of this course, but there is kind of a special mathematical formula that we can plug all these responses in order to determine someone's actual absolute threshold, an actual just noticeable difference threshold, as opposed to their thresholds that are kind of maybe biased by their own expectations. So signal detection theory does not subscribe to the notion that a person's ability to detect stimulus relies solely on the stimulus. It assumes that there is no single threshold, because at any given moment, a person's sensitivity depends on the decision that he or she makes. So whether to say that they did see or hear or smell or taste something, or whether they say that they did not. So now I want to talk briefly about subliminal perception. You've probably all heard the term before. And so basically what we're asking here is, can we ever perceive things below our usual sensory threshold? So is it possible for us to perceive things that aren't actually there, or are so low that we shouldn't really be able to perceive them consciously? So this question can be answered through an examination of subliminal perception. And it has been shown that we can detect subliminal stimuli. Our brain has been shown to respond to them, even if they aren't kind of within the realm of conscious awareness. So priming studies have shown that when words related to a particular personality trait were flashed subliminally, so kind of so quickly that the person couldn't actually tell you what they saw, people were more likely to later judge someone that they read about having that trait. Another example is that thirsty people have been shown as likely to drink more of a sweet beverage when they're primed with thirst-related words, and to find ads for drinks more persuasive. Something to keep in mind about this result is that these people were thirsty to begin with. So it wasn't really saying whether or not they would have a drink, it's just saying that they would drink more if they were primed with those types of words. So you might ask, based on those results, can subliminal priming be used to manipulate attitudes and behaviors? There was an advertising executive who claimed so. He basically said that if he put advertisements saying things like eat popcorn and drink Coca-Cola within movies, kind of like added them in subliminally during movies in a movie theater, that he actually was able to sell more popcorn and Coca-Cola products. This one actually turned out to be a hoax. And studies of subliminal tapes have showed placebo tapes to be just as effective. So for things such as weight loss or kind of quitting smoking, sometimes people will use these tapes that they listen to that supposedly have subliminal messages that are telling them to kind of decrease those behaviors or kind of influence their behaviors in whatever way. But it has been shown based on empirical research that making somebody listen to a kind of a placebo tape that doesn't really have anything on it does seem to have about the same amount of effect. So some psychologists believe that these failures have left out an important aspect of subliminal persuasion, which is motivation. So overall, what I want you to kind of keep in mind about this is that there doesn't really seem to be a reason to be kind of scared of subliminal persuasion. So advertisers are actually far better off using more overt means, so trying to sell you their products directly, because subliminal ads will not make you do or buy something that you normally wouldn't. So that's kind of our main takeaway here, is that they might influence, for example, the thirsty people to drink more, but if you were completely not thirsty, you probably still wouldn't, go out and buy a drink. So it does have a lot to do with your motivation as well. Now we're going to talk a bit about the Gestalt principles of perception. So obviously, in perception, we must be able to tell where one thing ends and another begins. So Gestalt psychologists, and I mentioned them way back in chapter 1, study how we organize the world visually into meaningful patterns and units. So if you remember from what I said back then, to them, the whole is greater than the sum of its parts. So it's kind of about the bigger picture. Gestalt psychologists use a number of principles to describe how we organize perceived features from our environment. An example of which is that people tend to organize the visual field into figure and ground. So for example, if you were looking at a picture, and it's sad I won't be able to kind of draw these. Usually I kind of draw these on the chalkboard when I talk about them, but I'll try to explain them as best I can through here. But basically, if you have a picture, there's always going to be something that's kind of the focal point of the picture that stands out to you, right? So for example, if you see, a picture of a bowl of fruit sitting on a table, you would probably consider the fruit in the bowl to be the focal point of that picture. And so therefore that fruit in the bowl would be the figure, and then everything else in the background, whether it was the table and the walls and whatever else, that would be considered the ground. So you can think of background as kind of the background. This can also apply to sound as well. So if you're listening to a song, for example, you tend to kind of listen to maybe like the singer's voice, and they tend to stand out to you relative to the instruments and kind of everything else going on in the song. So figure and ground just basically says that usually there is kind of one focal point or one figure of a picture or a song or whatever, and then the rest is kind of like the background. So figure may stand out due to its intensity or size, its location in the scene. So usually if it's in the lower half of the picture, it's more commonly where the focus lies, its uniqueness, or its movement. But sometimes it is ambiguous. And so I'm sure you've all seen examples, and I'll show you one in a minute, where it's very difficult to kind of decide what aspect is the figure and what aspect is the ground. Other Gestalt principles, and we'll talk about each of these individually, include things like proximity, similarity, continuity, and closure. So here in example A, we see figure and ground. This is a very good example of where the figure and ground are a little bit more ambiguous. So in this case, if you look at the black part of this picture, you're probably going to see a vase if you're focusing on the black part. However, if you focus on the white part of the picture, you probably see two faces that are staring at each other. So this is an example of, depending on what you focus on, the figure, or like kind of the main focal point of the picture, will change. So when you are focusing on the black area and seeing that vase, in that instant, the vase is considered the figure, and then the white would be considered the ground. However, if you are staring at the white and you see those two faces, in that instance, the faces are the focal point or the figure of the picture, and the black would be considered the ground or the background. We also have proximity, which help us to group items together so that we can see items that are closer to each other in proximity kind of tend to be grouped together. We have similarity, which is when we perceive similar items as kind of belonging to a group. So we would see them as yellow and red lines rather than kind of individual yellow, red, yellow, red, yellow, red. In continuity, we see that even though technically, if we look at this as kind of like a black maybe wire that's twisting around a pole, even though we only see two pieces of black, we kind of continue them on in our mind. So even though it seems like two separate pieces, we would kind of see it as continuing on behind the pole and wrapping around. And then finally closure, which is when we look at an object that isn't fully filled in or kind of connected, we tend to be able to fill in the gaps with our minds. So I went over them very quickly just then because I have an entire slide on each, so we can kind of go through them in a bit more depth. So here's proximity. So proximity is basically saying that we tend to treat two or more objects that are in close proximity to each other as a group. So you can see these examples here. If you look at those red dots, you're more likely to say that you see 3 groups of 4 red dots, right? So we would group them based on how close they are to each other. In the second picture, the blue dots, we'd be more likely to say that we see columns of blue dots going down rather than rows going across. And that's because the dots that form a column are slightly closer to each other than the dots within each row. Another real life example I like to talk about is eggs. So if you looked at a carton of eggs, you're much more likely to say that you see 2 rows of 6 eggs rather than 6 rows of 2 eggs, right? Or 6 columns of 2 eggs, because the eggs that are next to each other in that row of 6 tend to be a little closer together than the eggs that are kind of across from each other in those 2 rows. For similarity, we tend to group based on similarity in things like color, shape, or orientation. So for example, when you look at these pictures here, you should see pretty clearly in the first picture that there is kind of an X that's created out of circles, and it seems to be kind of on a background of blue squares. And so the fact that we're able to kind of take those and group them together and see that X as opposed to seeing, you know, circle, square, 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 circle, square, circle, square, square, like the fact that we actually see a pattern there is based on the principle of similarity. So because the circles are more similar to each other than they are to the squares, we perceive them as kind of being grouped together. The same thing in the second here. This one is an example of coloration and similarity. So we see that some stars are red and some stars are white, and we tend to be much more likely to group them together as rows of alternating red and white stars, as opposed to kind of looking downwards and saying, okay, well, it's red, white, red, white, red. So we tend to group them again based on their similarity, this time in coloration. And another real world example for this one is sports teams. So if you are watching, say, a game of hockey and you have players from 2 different teams, you're probably grouping them together based on their uniforms that they're wearing, right? So you're able to tell which members are within each group, so which members are on what team, based on the fact that they are wearing uniforms that are different in color or whatever else. And so in that way, you are grouping them based on the color of their uniform. For continuity, we tend to view items as whole figures, even if the image is broken into multiple segments. So for example, a lot of people would say for this first picture here, that they perceive it as a line that keeps continuing, that kind of passes behind the oval. Most people don't see it as a line and then a curved line and then a straight line again. They see it as an oval that is kind of sitting in front of a line. So we perceive it as continuing on behind the oval, even though we have no proof of that. The same thing in the other picture here, even though it's just a bunch of dots, a lot of people perceive them as kind of 2 separate lines. So one that's kind of curved and the other one that's like a straight diagonal line. And so we kind of perceive them as kind of continuing within their pattern rather than kind of being a bunch of meaningless dots. And then finally for closure, and this one's probably honestly the simplest one to explain, we tend to view items as whole figures by filling in the gaps to complete a whole object. So obviously if you're looking at this triangle here or the E, we still perceive it as a triangle or perceive it as an E, even though technically it's not because they have a little gap in them. With the face, we can kind of perceive that as someone's face, even though there's nothing up at the top for the head. So our brain kind of does the work for us in these instances, and it kind of fills in the gaps in order to complete a whole object. So now I want to talk briefly about top-down and bottom-up processing. So we're almost finished with this module, and then the next one we'll move on to vision. But these things that we're talking about in this module are kind of general characteristics that will help you understand the stuff in the other 3 modules in this chapter. So human beings typically take one of 2 approaches in order to perceive our world around us. We either engage in top-down processing, which occurs when prior knowledge and expectations guide what is perceived, or we engage in bottom-up processing, where we're constructing a whole stimulus or concepts from bits of raw sensory information. So in that case, we'd perceive the individual bits and use them to construct a more complex perception. So an example of top-down processing might be looking for a friend in a crowded room. So you don't just kind of scan the room and look randomly at people. You have an idea in your mind of who you're looking for, right? So in that way, you're engaging in top-down processing because you already have in mind what you're looking for, and you're basically searching from that kind of image in your mind. Bottom-up processing might occur, for example, when you're driving a car in a foreign country. So if you've never driven in that country before, there are a ton of rules and things for you to remember and keep in mind. So you're probably more likely to kind of put all those little rules together and kind of collect up all the things you've learned about driving in this country in order to kind of process and perceive how you should be kind of engaging in driving within this country. So how we perceive the world is usually a combination of both processes. We don't usually use just one or the other. But it is true that when we see something for the first time, we typically use that bottom-up processing because we're trying to put all the individual components together to kind of create an overall perception. Or we might be surrounded by certain cues that influence our expectations. And so in that case, when you kind of have an idea of what you're looking for based on cues, that will be considered top-down processing. So if you look at these figures here, in figure 4.6, this is a really good example of top-down processing. So if you start reading across and you see 12 and then 13 and then 14, you're probably perceiving that middle term to be a 13, right? Because you're using the surrounding information, so the 12 and the 14, to guide your processing of that middle term. And so in that case, you're likely to see it as a 13. However, if you look A and then C, then using that context, so using those cues to guide your processing, you're more likely to see that middle term as a B. So it's kind of an ambiguous term. It looks like both a B and a 13 at the same time, but depending on what cues you're using to orient yourself, you might perceive that middle number or letter as something different than somebody else. So that's a great example of top-down processing because it's showing you how the information that you already have available is helping guide your processing of that middle term. Figure 4.7 is really interesting. So this shows us how expectations can influence our perception. So if I show you this picture and you have absolutely no context as to what's going on, you have no choice but to engage in bottom-up processing, which is basically taking all those individual lines that you see within this picture and kind of fusing them together in some way, so using kind of that principle of closure to determine what it is you're looking at. But if I said, do you see an animal in that picture? You are probably much more likely to tell me that you see a rat then. Because if I gave you that clue of saying, you know, do you see an animal, then that's going to influence your perception and you might engage in that top-down processing instead. So instead of just taking every single thing as individual and kind of like piecing it together in that bottom-up fashion, if I said, are you looking at an animal? Or if I showed you a bunch of pictures of animals before I showed you this, then you're much more likely to use those cues and engage in top-down processing and tell me that you see a rat or a mouse here. However, if I showed you a whole bunch of pictures of faces before I showed you this, or if I asked you, do you see, you know, someone in this picture, you are more likely to use those clues to conclude that what you're seeing in this picture is actually a man's face. Now, I appreciate that maybe you don't see both those ways. I can't, unfortunately, really, usually, again, I would kind of be pointing at this and showing you what's going on. But if you look at kind of the piece that bumps out the furthest to the left, you can see that that would be considered the mouse's head if you look at the little kind of black spot next to it as the mouse's eye, or you can see that might be considered as the man's nose if you look at kind of the circular object above it as one of his eyes. So If I asked you to look at this and give me your interpretation without any explanation, you would probably be equally likely to say a man's face or a rat because you have no context, so you'd be using that bottom-up processing. But if I was showing you a bunch of pictures of faces or showing you a bunch of pictures of animals beforehand, you're much more likely to engage in top-down processing and therefore see either the man or the face depending on those cues. Or sorry, the man or the rat, depending on the cues that I gave you. So finally, I just want to talk briefly about attention and perception. So it is true that we can engage in selective attention, which basically involves focusing on one particular event or task. So it tends to prevent us from being overwhelmed. So for example, if we're studying or driving without distraction, that would be an example of using our selective attention. So we're fully focusing on that one task. However, a lot of us engage in what's known as divided attention, which involves paying attention to several stimuli or tasks at once. So maybe you're driving while listening to music or driving while talking to a passenger. So in that case, your attention is divided in some way between the two or more tasks that you're engaging in. And whether we choose to attend selectively or divide our attention depends on the familiarity or complexity of the task. So for example, the very first time that you got into a car and drove, you probably paid a lot of attention to exactly what you were doing. So you're probably being very selective in terms of your attention, because at that point, that task was very complex to you and you felt like you needed to devote your full attention to it. However, as you became more familiar with driving, maybe you ended up driving a lot and you've been driving for years now, you're probably more likely to be able to engage in divided attention when doing something like driving. Because when you're at the point where that task kind of comes automatically, then you're able to kind of focus on other things simultaneously. So things like how familiar or complex a task is will influence whether or not you have selective or divided attention, as well as our mental energy level. And so it's important to note that there's no such thing as a good or a bad multitasker. In general, results of studies on multitasking, from what I've seen, do show that it is not overly effective. You might be able to kind of focus on two things and accomplish two things at once, but a lot of the time it comes at some cost to one or more of the activities that you're engaging in. And one other important thing to note is that selective attention can at times lead to inattentional blindness. So if you followed my instructions and watched that video at the beginning, I'd like to ask you all now how many of you actually saw the gorilla. And obviously it's a rhetorical question. I know you're not going to be able to answer me right now, but I can definitely tell you that the very first time I saw that video, which was in my intro psych class years and years ago, I definitely did not notice the gorilla walking right across in the middle of everyone. So it's just a really neat example of how sometimes if you're paying too much attention to one task, it can lead to what we call inattentional blindness, which is actually a failure to notice clearly visible events or objects because attention is directed elsewhere. So because you were so focused on counting the basketball passes, you may have failed to notice the gorilla walking across the screen. And that is the end of Module 1. So this is for Monday, November 23rd's class. If you have any questions, please let me know. I'll be in the chat tomorrow morning. And other than that, I will see you in the next video. So next we will talk about vision. Have a great day, everyone.